Hello everybody and welcome to part B. This is the continuation of example 3 on page 152 of the workbook. This is the same set of data that we looked in part A, so this is time and temperature data that we're looking at. In part A we calculated the line of best fit, and what they're asking us for here is the quadratic equation of best fit. Okay, so it's asking us to find the best fit parabola that goes through this data. Okay, so just to give you kind of an idea of a picture of what we're trying to do, let's scroll back to the data itself on the previous page. Okay, so you can imagine what we're looking for is a parabola that kind of goes through here and gives us the least error possible. Okay, what would the best way be to draw that parabola? That's what we're trying to figure out. And the nice thing is we can use this same matrix technique that we used, okay, to do a parabola or any n-degree polynomial. The only difference is that our matrix is going to be bigger. Okay, so let's remind ourselves first of what kind of the standard form for the equation of a parabola is. Okay, if there were a parabola that went through all of these data points, it would look like that for some constant c, d, and f. Okay, so if we start with the assumption that there were, the hypothetical assumption that there were a parabola that went through all of those data points, we'd start by observing that the first output value we would get by plugging the first input value into our function. So we'd get c times 1 squared plus d times 1 plus f. And then we just do that for all the rest of the data points. 2 would be c times 2 squared plus d times 2 plus f. Okay, we keep going until we get to our last data point. All right, and we can rewrite that in matrix form, just our matrix is going to be a little bit bigger this time. Okay, so this time our matrix would look like the first column would basically consist of the squares that we're seeing over here. Okay, so 1, 4, 9, 16, and 25. Then the next column would be just these numbers. So 1, 2, 3, 4, 5. And then the last column would just be ones. All those f's are getting multiplied by 1. Okay, we don't know what c, d, and f are. Okay, and over on the right-hand side would be our output values, 1, 2, 4, 5, and 8. Okay, and just to kind of match up the theorem notationally, we've been calling this matrix A and this output vector y. And the key, just as before, was calculating the matrix A star A and the vector A star Y. That's kind of how this theorem works. All right, so let's start with A star A. So we need to take the transpose of our matrix A. Okay, this is a little bit of writing. Okay, there's the conjugate transpose. We need to multiply that by A, the matrix that we started with. Okay, and if you do the multiplication there, you're actually going to get a 3 by 3 matrix that looks like this. Okay, I'll let you confirm these calculations, and you should feel free to use a calculator when you're doing this. If you've got a calculator that multiplies matrices, wonderful. Okay, notice the difference between part A. We got a 2 by 2 matrix, so finding a parabola of best fit just increased our matrix up to a 3 by 3. Okay, now the other calculation that we need is A star of y, A star times y. Okay, so that's this same big matrix. Okay, this time times our right-hand side, 1, 2, 4, 5, and 8. Okay, and if you do the multiplication this time, you're going to get a vector that's 3 by 1, 325, 77, and 20. Okay, and so we've got a system, 3 equations and 3 unknowns that we need to solve that starts out looking like this. Okay, and if we write that down in matrix vector form, it's going to look like coefficient matrix equal to this guy up here. Okay, and then we'll augment it with the right-hand side that looks like 325, 77, and 20. Okay, and that's a problem that you'd probably want to take to a calculator to solve. Okay, you could do it by hand. It wouldn't be too horrible, but it would take a little bit of time. And our solution ends up looking like this: 3/14, 29/70, and 2/5. Okay, and so what we wind up with here is a parabola of best fit that looks like this. T is 3/14 t squared plus 29/70 t plus 2/5. Okay, and one thing I'd encourage you to do, if you have a graphing calculator, graph this parabola, see what it looks like, okay, and see if you think it fits this set of data points well. Okay, and there's one last thing that we could do here. We could calculate the error and get a sense for how good a fit our parabola is to this data. Okay, the error by definition again is the square of the length between ax0 minus y. Okay, and again, I'm gonna be rude here and let you do that calculation. Take the matrix A and just substitute in the various pieces and just show you what you wind up with if you do that. 0.457. How does that compare with the error that we got before? Okay, there with the line we got a 1.1. Okay, so we got a smaller number for the parabola. You might think about what that means in the context of this problem.